Hi guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to be taking a look at the RX 5700 XT Nitro Plus OC PCB from Sapphire. So, I guess the summary of how this PCB performs is it's basically a side grade to the reference card and completely average in every other way. Which admittedly is better than most RX 5700 XTs, which are just straight down, so they are downgrades, but very minor downgrades compared to the reference PCB.
Before that, this video is brought to you by Thermaltake's C360 DDC hard tubing water cooling kit. If you're ready to dip your toes into the water and build your first open loop cooling system, the Thermaltake C360 DDC hard tubing kit comes with all of the components you need. The kit includes a 360mm radiator, 3 120 ARGB fans, a copper W4 ARGB water block for the CPU, a pump and res DDC combo, and all the fittings needed to build a full CPU open loop. Learn more at the link in the description below.
Let's just get right into it. And so the first noteworthy addition on this card compared to say like a reference card or most other GPUs is that Sapphire has all of these fuses all on the card for basically every single one of the power inputs. So for the 12 volts of the PCIe slot right here, then for the 3.3 volts, which was on the front of the PCIe slot, then of course we have for the two 8-pin power connectors as well. Now the thing is, these fuses, they're mostly there for like helping repair, like helping in an RMA situation, not really to prevent damage from the card, because the fuses are very unlikely to be fast enough to actually prevent any damage. They're more like the thing is, a lot of the time you get sort of component failures where it's like, well, one thing fails and then it can spread and get worse from there. So the fuses can sort of prevent the spreading part of the damage. But they're not really going to prevent the initial, like, you know, a power stage blowing up or something. Like, the power stage is first going to die, and then the fuse is going to trip. It's not going to be the fuse tripping before something's already permanently damaged. But the thing is, on cards without the fuses, if a power stage dies, it's actually very easy to then like keep power cycling the card to death, where you'll potentially not only have the dead power stage, but then like a dead GPU core as well, or a dead set of memory, or dead whatever else is on the other side of the power stage, really. So it's kind of the thing. So the fuses can sort of prevent damage from spreading. They don't really prevent damage from occurring. And so the main use of these is like if you send the card in for repair to like Sapphire, you know, through the warrant, basically if you RMA the card, Sapphire might have an easier time repairing the card or figuring out what the fault with the card was than if there wasn't any fuses. But yeah, as an end user, I would basically ignore that these exist, because ultimately, like, regardless of if the card has fuses or doesn't, you're still going to be sending it back to the manufacturer if anything trips those fuses, right? Like, that's kind of the thing, is if you had a card that doesn't have the fuses, then you'd still be sending it back to the manufacturer because it probably wouldn't turn on anymore. So yeah, that's kind of the thing. With the fuses is just like that, you know, they don't hurt anything, but they really don't, in my opinion, they don't really add a lot of value to the card. But they are there, and, you know, I assume Sapphire really likes the benefits that they give to them when it comes to repairing the card. So we do have all these fuses. We also have a dual BIOS switch, and our two BIOS chips right down here, or at least I assume those are the BIOS chips, because there's not really anything else BIOS chip shaped anywhere else on the card. They generally look like that. So yeah, and there are two identical chips right next to each other, and so it's like probably the BIOS chips. But anyway, so it does have dual BIOS. There's a third position on that switch, which allows you to use the Sapphire Trick software to choose between your BIOS chips. So yeah, it's basically a slightly more advanced dual BIOS implementation, I guess. And like, it doesn't hurt anything, but like, it's kind of like the fuses in my opinion. And especially with a 5700 XT, it's not like you can really do much with BIOSes on these cards. So to me, this doesn't I don't really consider this that special. But anyway, so that kind of covers the not VRM parts of the card. So let's take a look at the VRM. So this right here is the V-Core VRM. And, well, it's a 1, 2, 3, 4, 5, 6, 7, 8 phase, which means it has one phase more than the reference card. The way Sapphire actually gets all of these extra phases is by running the IR35217 in a 4+1 phase configuration, where that 4 then goes into a bunch of IR 3599s located on the back of the card. So if we just go to the back of the card, that's these chips right here. So those are your 3599s. Those are doublers or quadruplers, depending on how they're being used. But here they're being used to double. That's why there's 4 of them to get 8 phases. So yeah, those do ×2. They do not actively current balance, but international rectifier controllers are actually smart enough that they can distinguish between the 2 phases on a single current sense input and current balance them that way. So yeah, it's not really basically it's a difference in how the current, like some manufacturers like say Intersil or On Semiconductor, they actually have power, like their doubler does the current balancing. But International Rectifier actually has the controller current balance through the doubler, which is which is why their doublers are dumber than everybody else's, because it's like, well, the controller can just do it on its own anyway, regardless of if there's a doubler, like through the doubler anyway. So yeah, because it can still distinguish between the 2 phases. That's kind of the main issue. Is on some other controllers, like you can't tell if you have 2 phases on one current sense input. It's just going to see the combined current of both phases at the same time. It's not going to be able to tell if like phase 7 or phase 8 is pushing more current. So you're not going to necessarily get perfect efficiency if the current without we're having some kind of current balancing, you're not going to necessarily get perfect, the best efficiency you could out of your, multi-phase design. So anyway, this is this is very much still an 8-phase, right? Because we do have 8 phases interleaving. So you only ever have one. Well, in steady state operation, you'll only ever have 1 phase on at any given time. Now, doublers do add a very small amount of delay to your PWM signals, which means that the transient response is it is slightly affected, like very slightly. Like we're talking couple millivolts. You can measure it. It probably doesn't make any difference in the real world. But yeah, so they add a little bit of delay to the PWM signal, which basically means the VRM is slightly slower to respond to changes in output current, which means your transient response is slightly worse. But generally speaking, like you can compensate for things like that with different, capacitor configurations on the output. So I wouldn't really I don't consider it a, concern-worthy thing to worry about. It's just like, it's a thing that happens. That's it. Right. Anyway, so, that's how Sapphire is getting their 8-phase here. And, if it was just like an 8-phase, that would be all fine and good, because at least it's 1 phase more than the reference card. But the thing is the power stages. So Sapphire's opted for a bunch of NCP 302155s. That's not, I don't know why I'm having such a hard time writing 21 today. Seriously, I've done a couple takes of this video and I get to the 21 of the part number and it's an 11. It's never a 21 is basically what I'm getting at. Anyway, so these are 55 amp power stages from On Semiconductor. And this is kind of where it's like, I'm really not impressed with this PCB, because the reference card is 7 70 amp smart power stages. This is 8 55 amp regular normal power stages. So they basically, they do have an over temperature protection built in, but they don't have built-in temperature monitoring. They don't have built-in current monitoring. They don't have basically anything that would make them smart. So yeah, that's kind of the thing with these, is just like they're plenty efficient, right? Like that's still a 55 amp power stage. That's not like, up until recently, a 55 amp part was like the second best thing you could get to a 60 amp, right? Like, and it still is second best to a 60. It's just like 60s were as high as it, like you couldn't buy better than 60 amp power stages for a very long time. But now you can get 70 amp smart power stages and even 75 amp power stages. And it's just like, yeah, 55 isn't that great. And the bigger issue is just like the 7-phase VRM of the reference card is actually, because it uses those really nice 70 amp smart power stages, it's really efficient. And this VRM is ever so slightly worse, which is true for most RX 5700 XTs that don't use the reference PCB, with the exception of like the Red Devil and the Strix and maybe the MSI Gaming X, because I don't know the spec of the parts on that one. So yeah, everything else is just like slightly worse than reference. Not bad enough that it's actually like concern worthy. It's just like, if you were buying a card for its PCB, and not like if you didn't care about the cooling system it comes with and you just were buying the card for its PCB because you're going to do like extreme overclocking or water cooling or something like that with like a core only water block, then it's like Strix, Red Devil, reference card, and then this. Like after I'd rank this after the reference card. So yeah, it's just not like, well, it's that's the thing is like AMD. The thing is the reference card from AMD is really not what like if you look at that design, it's not very well cost optimized. Like there are 70 amp smart power stages in places where they barely like they don't really make any sense. There's two IR35217s which are really expensive voltage controllers for like there's two of them. Like when you only need one, as is shown by every single other RX 5700 XT PCB out there. And yeah, so I understand why nobody likes you. Like the reference PCB is only used on the reference blower cards, but that doesn't change the fact that the reference PCB is just better than all of like basically all of the custom PCBs that we've seen, except the Strix and the Red Devil. Now, admittedly, this card right here could have actually been on par with the Red Devil because the Red Devil is basically, so this is an 8-phase of, NCP 302155s. The Red Devil is a 10-phase of NCP 302155s. So yeah, it's like, I'm really, really disappointed that Sapphire didn't actually include these two phases. Like, because these power stages right here, if you check the price for these at a third-party distributor, which those third-party distributors charge more than the original like if you're buying enough volume for like GPU manufacturing or something like that, you can go straight to the manufacturer. You can get even lower prices. But these power stages are $1 a piece. And the inductors are very unlikely to be more than $1 a piece either. So basically by, not including these two phases down here, Sapphire's maybe saving like $4. And that's just like, really? Like Power Color spent the $4 on their extra, two phases. And well, we're not going to talk about the Strix because that card's insanely expensive, but like that one goes out of its way to use some top of the line parts. And then, yeah, and then there's basically everybody else where the PCBs vary from slightly worse than the reference card. Well, it's basically varying levels of slightly worse than reference, right? So it's kind of the thing. And the Nitro, unfortunately, falls at the very top of the slightly worse than reference pack. So it's like the least slightly worst. But yeah, so let's talk about the efficiencies, because the efficiency still isn't bad. It's just like the reference card is ever so slightly more efficient, and then there's cards, like the Red Devil and the Strix that are even more efficient. But yeah, so 1.2 volts output voltage, 500 kilohertz switching frequency, and a 5 volts drive voltage, because that's what these run on. And I really didn't space that out well, did I? So whatever, we'll just 5. Okay, look, we're just going to squeeze it in like that. So 5 volts drive voltage, because that's what just these power stages run on, which is probably produced by this regulator right here. That's very likely the 5 volts rail. You don't really need to worry about like this isn't a concern-worthy rail. It's just like, yeah, it exists. If the card doesn't work, then maybe this might not be working, right? Like it's the kind of regulator you only care about if you're actually repairing the card and not if you're like overclocking the card, because you're not going to put more load on it. Anyway, 1.2 volts, 500 kilohertz, 5 volts drive, 150 amps output. You're going to be looking at about 15 watts. And the interesting thing is actually basically all of the 5700 XTs do this right here. Pretty much, I think the Strix might actually be a tad better, like might be the only one which does a little bit better here, and the Red Devil might be like 14 watts instead of 100 instead of 15. But everything else is basically sitting around that 15 watt mark. Then doing 200 amps output, this PCB will this VRM right here should kick out about 21 watts of heat, whereas the reference card should be around 19, and some of the cheaper, like basically what most other 5700 XTs have is this for their VRM. So, the remaining 7 phases of this 8 phase, those would be producing around sort of 23 watts of heat. So, yeah, basically this is not a significant upgrade or a significant downgrade for it's not a significant upgrade over the other cards, and it's not really a significant downgrade from the reference card, but it's just like, it's very average in my opinion. It's just, it's not great. It's not terrible. It's not going to blow up on you or anything like that. It's just like, from a Nitro, I was kind of hoping for more. right? And I think maybe Sapphire is probably holding back because they're planning like a Nitro limited edition like they did with Vega, or maybe they're planning there was rumors earlier in the year that there would be a Toxic edition, so maybe they're saving the full version of this PCB for the Toxic card. But honestly, compared to some Toxic cards of the past, that would not be that impressive. So yeah. Because like if you look at, well, more like the thing is the Toxic cards are kind of rare. So if you just look at like high-end Vapor X cards from Sapphire, like the 290X Vapor X that had basically twice as much V-Core VRM as what you got on the reference card, this is one phase more, literally just one phase more. And if you look at something like, say, the Vapor X Toxic, that was also like an insane upgrade over the reference card. And it's just like, yeah, and then there's this card where even the thing is, even the regular Vapor X was a slight upgrade over the reference card because it basically took the reference VRM and added a whole extra phase without changing out the component quality. Whereas this, it adds an extra phase, but it downgrades the power stages to sort of like, I don't know why they didn't just, well, no, I assume the 70 amps more power stages are just straight up more expensive, are significantly more expensive than these. So these make far more, like 8 phases worth of these is still cheaper than 7 phases of the power stages AMD used on the reference card. But yeah, it's just like, I'm really like, I don't know. I feel like the Nitro should be maybe. Like, the thing is, it's not really, like, Sapphire doesn't do extreme overclocking parts, so I guess you can just, yeah, it's a gaming card, right? The main focus is that it has an RGB header and that there's RGB bling on the back, so I guess the fact that I don't like the VRM is like, nobody actually cares. Anyway, 250 amps output. You're going to be looking at about 28 watts of heat. So, some of the 7-phase cards put out a bit over 30 watts. The 10-phase cards put out around 25, I think, off the top of my head. So, yeah, that's the thing. This VRM right here just isn't really that impressive. It's also not bad, right? Like this, like the air cooling, like the cooling system this card comes with for its VRM is easily going to handle this kind of these sort of heat output levels for the VRM. And if you're on ambient cooling, you're very unlikely to exceed 250 amps like ever in terms of core current draw. So yeah, like for the daily gaming setup, yeah, this is a totally acceptable VRM. It's just that I was really kind of hoping for more, and I didn't get it. Anyway, going up to 320 amps, which normally I go up to 300, but the thing is, these power stages at the data sheet ends at 40 amps output for the heat outputs. So because the thing is with like any power stage, like it might be, it's a 70 amp smart power stage. That means if you have one hell of a heatsink on that one power stage, it can do 70 amps. If you have 10 of them next to each other, you're not getting 700 amps output out of that because it'll produce a stupid amount of heat. And the same is true of basically any power stage. So these might be, like capable of 55 amps if you have one of them sitting isolated all on its own with its own heatsink. But, in a multi-phase configuration that kind of doesn't work at all. So for practical uses, usually the data sheets stop a couple 10 20, like normally around 10 amps before the actual sort of spec, like the performance class, I guess you could consider it, of the power stage. Because like at the full current handling capability, the heat output is just it's impractical amounts of heat. So you don't actually design with that level of heat ever. You don't design with that assumed current draw through the power stage ever, right? It's just like, yeah, it could do that if you were really desperate. So anyway, since these top out at 40 amps, what is the maximum sort of heat output that the data sheet specifies as well? 320 amps, you'd be looking at about 45 watts of heat, which is not bad for 320 amps. I can't actually remember how, it's a bit worse than the reference card again, and it's a bit worse than the Strix, and you get the idea, right? But it's not a significant downgrade. And the other thing is like 320 amps, I'm 99% certain you'd have to be on liquid nitrogen to get anywhere near that. If like the other thing is that AMD cards don't necessarily scale that well with liquid nitrogen, so you might not even be able to hit that kind of current draw even on liquid nitrogen. So, the fact that the VRM would produce 45 watts of heat at 320 amps output could be pretty irrelevant, right? Like you're not actually... It's more of a theoretical, like, yeah, if you did that, it would produce this much heat, but doing that is very unlikely. So yeah, honestly, so for like a 57, like for what I think the intended purpose of the card is, which is obviously just sitting on the stock, like most people are going to be buying this card for the air cooling system it comes with, right? Like if you're buying a card for water cooling, there's the reference card, just go get that. So if you're buying this card for the air cooler it comes with, well, you're going to be in this range, and there the VRM performs just fine. So yeah, you really can't complain. Like, you know, from a normal perspective, you can't complain. If you were hoping for some super premium PCB, this is not it. But yeah, it's not bad. It's just like not better than reference, and that's kind of that. It's just Sapphire. I'm sad because I'm used to, like, I have a very concerning collection of Vapor X cards, so that's why I'm sad about this VRM. But yeah, it's, you know, it is what it is, and it's not terrible. It's just also like, you buy this card for the heatsink. You don't buy it for the PCB, and that's fine, right? Like the VRM is not so bad that it'll blow up or anything like that. It's just, it's also not an upgrade. Anyway, so moving on, minor rails, we've got what I assume down here is the SoC. Up here we have the two-phase memory power, so VMEM, and this is like the first card where the memory VRM isn't like completely split. And I guess like, well, it's kind of I assume the decision to basically have one phase on either side of the memory chips is to basically get better power distribution through the GDDR6 power plane, because this is this is a noticeable thing on a lot of cards where you'll have, say, the memory VRM up here, and then you'll actually end up with like memory bulk capacitors down here because, well, if this memory chip suddenly needs a bunch of current, it's not going to be able to get it because it's on the other side of the power plane. So you need to add some capacitor, like actual bulk capacitance near to the chip instead of just, you know, the usual little multi-layer ceramics like that. So yeah, and even this card, which, you know, takes this is one of the more unique layouts for the memory power. Yeah, it still keeps the sort of split output instead of having a two-phase that's like jammed in the corner, which is pretty typical for a lot of other cards. And that basically just means that, you know, power distribution is more uniform across the memory power plane. Instead of having sort of, like, what tends to happen is you'd basically have slightly higher voltage in one corner than the other. Which most of the time isn't a concern, but I guess with GDDR6 running, like with the speeds that GDDR6 runs at, maybe because of the memory controller from AMD, all the 5700 XTs end up with this kind of power, like, well, except the Strix. The 5700 XTs end up with some sort of, you know, weird memory VRM configuration like this. Which I assume is because of some kind of power delivery requirement, because there's not really any practical reason to do it this way otherwise. Anyway, so that's the memory VRM. And then over here we have what I suspect is the VDDCI. So that's the memory controller power. And all of these, like SoC rail, VDDCI, VMEM, all of these just use more of the NCP 302155 power stages. So the memory VRM, you know, this could spit out up to 40 amps and produce only about 4 watts of heat while doing that. So, you know, total, like, very much overkill for powering just a bunch of GDDR6 memory chips. But it is worth noting that the reference card actually goes for more 70 amp smart power stages in its memory VRM, which is another one of those things with the reference card where it's like, evidently AMD just didn't care how much it costs to build that, because you don't none of the other cards do that. Like, everybody else uses a cheaper, you know, more cost-effective component for their memory power, and then there's the reference card where it's like, yeah, we're going to use 70 amp smart power stages for the freaking memory VRM and VDDCI and SoC. So yeah, and that's just like the reference card just has some sort of really not cost-effective design decisions like that. Which is, I guess, why you know, it's restricted to just the blower cards, because as soon as anybody designs their own heatsink, they're like, we are not paying for AMD's PCB. It costs too much. Anyway, VDDCI, you know, well, that's one phase. This is a two phase, right? Two like that. VDDCI is a one phase, so that one can spit up to 20 amps with a little under 2 watts of heat output. Same goes for the SoC, because again, that's just another NCP 302155. So yeah, these are all plenty powerful for what they need to power. VDDCI and VMEM, or at least what I assume is VDDCI, is because the thing is, I'm not sure if VDDCI is up here or if it's down here, and like the SOC and VDDCI might be switched around. I'm not 100% certain on that. But anyway, whatever these three phases up here are all controlled by this controller down here, which is an NCP81022. This controller is kind of neat because there's a full public datasheet for it, and it's super easy to mod. So if you wanted to tweak some of your, like whatever this rail is, if you wanted to tweak the voltage of that, very easy to do. If you wanted to tweak your memory voltage, very easy to do. The funny thing is, I'm not sure, like, I've not had any, like, I've not played with a 5700 XT myself at all, mostly because I don't feel like I have time for messing around with GPUs right now because I have too much other stuff to do. Yeah, but at least on NVIDIA cards, bumping up the GDDR6 memory voltage does help with memory overclocking. The thing is, with 5700 XTs, I would assume that the limit for memory clock is not the memory chips, but the memory controller, which could actually also scale for memory voltage, but yeah, it's kind of interesting. So it might make sense to bump like VDDCI, but the thing is like memory controllers are extremely fragile. It's like if I look at the list of my victims during overclocking, it's mostly memory controllers, and then like a couple CPUs where I forgot that they're at like 2 volts or something. So, you know, it's just memory controllers are like where it's, you know, you raise the voltage a little bit and suddenly your memory channel is gone and it isn't coming back because you just blew up that memory channel. Or, you know, the GPU starts artifacting out of nowhere and then never stops artifacting again because you raised the memory voltage by, you know, 100 or 200 millivolts. And you'd think that's not really that big a voltage increase, and then the memory system goes straight to hell. But yeah, this thing is super easy to mod if you know, are interested in breaking your card, in which case I would still advise that which actually, yeah, that's like, the reference card's actually harder to deal with because that uses another IR35217. Anyway, that's running in 2+1 phase configuration, so 2 phases for the VMEM and +1 for the VDDCI, and I do believe this controller goes, like, it's 4 phases on one of the outputs. I'm not sure if the second output it goes up to 2 or if it's just 1. But yeah, so it's not being fully utilized here. It's just running as a 2+1 configuration. So yeah, that's basically, oh wait, nope, forgot something. We can talk a bit about the capacitors. So this is another sort of arguably a cost-saving thing. The reference card uses a whole bunch of SMD aluminum polymers, which are expensive, and for the bulk capacitance on the output of the VRM. For the input capacitors, the reference card uses a bunch of tantalum SMD capacitors, which are more expensive. Like, aluminum polymers, expensive. Tantalum polymers, well, aluminum polymers in the SMD package are expensive. Like, these are still aluminum polymers, they're just through holes. But yeah, tantalum SMD capacitors are a step above your aluminum polymer SMD capacitors in terms of prices. So yeah, this is another thing that basically all of the custom cards do for cost saving reasons. And I think the reference card basically goes with the SMD, like the expensive SMD capacitors, because they need to accommodate the blower heatsink. It's not really like a consideration of, hey, we actually care about the capacitors being electrically superior, because they are. The SMD capacitors have better ESL, better ESR. Well, ESR you can get the same spec depending on what you're buying, but the ESL is vastly superior for the SMD capacitors. And the thing is like with the reference card, it's not really about like the electrical advantages of the SMD capacitors. It's mostly about the fact there's a blower heatsink, and you need to get that fan in the shroud somehow, and having capacitors sticking up off of the PCB tends to get in the way of blower fans. So yeah, not an option. So anyway, for the output, we have a bunch of Nichicon FP series capacitors. So Nichicon's a Japanese capacitor manufacturer regarded very highly. The thing is, I've not really heard of any, like, even like, because the input capacitors here are from APAC. And I've not really heard of like these are still aluminum polymers, and I've just not heard about those having like really high failure rates in general. So, you know, like, as much as these might like be like, oh, Japanese capacitors and therefore better, it's like, well, it's not like I've ever heard anything about these failing, right? Because like the thing is, aluminum polymers are just inherently more reliable than aluminum liquid electrolyte capacitors. And yeah, that means, you know, if even if they're made by a Taiwanese manufacturer, they're more reliable than the usual electrolytics, and they're actually sort of easier to get a good reliability out of than the liquid electrolyte capacitors. So anyway, but these are 8-pack capacitors rated for 5,000 hours, and these I actually don't know the hours rating for, but these look a lot like what Gigabyte uses, so I'm going to assume they're the same 10K hours rating. Otherwise, they'll be 5K, 5,000 hours rated. And yeah, so we just have aluminum through-hole aluminum polymers. Now, the interesting thing actually about the endurance ratings is the SMD aluminum polymers, you can't get them in endurance ratings higher than like 2,000 hours. They just straight up don't make them, which was, or at least I couldn't find any when I did a quick search for those on DigiKey. They just like max endurance rating is 2,000 hours at 105 degrees. So yeah, kind of interesting trade-offs. But the thing is, if your VRM just doesn't run so hot, right, you don't need really high endurance capacitors. So, you know, if you're water cooling the card, I'd still say the reference PCB is just the better option. But yeah, also the other thing is like getting a water block for this is probably like right now you can't even get a full cover block for this, but even if full cover blocks did become available for this PCB, I still wouldn't buy it for water cooling because you could just get a reference card, right? And the reference card is just better in terms of the, like, it's not much, like it's very slightly better, but it's still better in terms of the component selection and, well, you know, efficiency of the VRM and just build quality in general. So, yeah, but that's kind of the thing is like, you know, like the things that Sapphire added is like they added the fuses, they added a whole bunch of RGB LEDs over here, they added some RGB LEDs over here and a silk screen so that they can get the, you know, glowing logo on the back of through the back plate. And you have the RGB header. So, you know, like it's obvious that the priorities with this card weren't to build some crazy overclocking monstrosity. It was just like build a gaming card with a really nice air cooler. This is it, I guess. That this does that, you know. But yeah, if you were expecting this PCB to be absolutely amazing, well, it isn't. If they added those 2 extra phases on, then like it would have at least gotten into the same category as the Red Devil. And the thing is, the Red Devil's air cooler seems to be doing really well as well. So, you know, I'd say kind of, I don't know. Like either is a good option in my opinion. Like the thing is just like the PCB on this card is really not worth celebrating as far as I'm concerned, because it's just, yeah, it's not really that special in any way, shape, or form. So yeah, that's it for the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support us here at Gamers Nexus, we've got there's store.gamersnexus.net if you'd like to pick up Gamers Nexus merch like mod mats and shirts and other things. And then we do also have a Patreon. You can find a link to that down in the description below. And I run a channel called Actually Hardcore Overclocking, where I do other overclocking related stuff. So if you'd check that out, that would be awesome. Thanks for watching, and goodbye.